Hello, in this video we're going to cover section 2 of chapter 10, which is going to cover the periodicity of physical properties of the elements on the periodic table. So what we're going to talk about here is how the physical properties change in the periodic table and across the periodic table for the elements. Now we're going to talk about a lot of different physical properties, but for all of them we have to remember two things. Number one is that we will need to be able to explain why these properties change and what affects them. And number two is that we are going to need to be able to look at patterns in properties in order to do things like identify different elements. Now we are going to talk about a lot of different properties here. So make sure that in your notes, you're keeping good track of which explanations and which definitions fit which properties. We're going to start by talking about atomic radii, which is a plural of radius. And the atomic radii is something we've talked about in past chapters. Now, there are many types of atomic radii that are calculated because we could talk about the atomic radii of an atom, of an ion in an ionic compound. We could talk about the atomic radii of a metal atom or a diatomic atom. So there are going to be a lot of different definitions or slight different definitions for different radii, ionic radii, atomic radii. But essentially, they are all going to do roughly the same thing. We are going to divide the distance between the nuclei of two atoms that are touching or bonded in some way in half. The idea here is that if we have two identical atoms that are either ionically bonded, covalently bonded, or some kind of bonded, and we measure the distance from the nucleus of one atom to the nucleus of the other, and we divide that distance by half, that should give us the radius of one of the atoms. Now, why do we need to discuss atomic radii? Well, that's how we discuss the size of an atom. We cannot just talk about the size of an atom by itself, because atoms are not a perfectly spherical thing. They're not perfectly tangible. So we instead discuss the radius based on this definition. Atomic radii for most elements is measured using the definition of what we call the covalent atomic radius. And that will be half the distance between the nuclei of two covalently bonded atoms of the same type. Now, this is very convenient for nonmetals because we can always covalently bond nonmetals. But for something like a metal, for example, we will use the metallic radii. Again, same definition. It's just half the distance between the nuclei of two touching atoms, but with a metallic radii, they will be metallically bonded instead of covalently bonded. Some elements may not be able to have a covalently bond and therefore not have a covalent atomic radius. And so other measurements of atomic radius can be used. One of them is the van der Waals radii, which would be for atoms that are held together by intermolecular forces, and like I mentioned earlier, the metallic radii. These are going to be measured the same way. Again, it's just half the distance between the nuclei. It's just, again, going to involve different bonds or different forces of attraction between the atoms that are held together. So now that we got the definition out of the way, how does the atomic radii change across the periodic table? We discussed this earlier in the year in a prior chapter, but patterns of atomic radius are very straightforward, and they are going to be dictated by the same basic properties that we talked about in, I believe, was chapter 3. Might be mistaken. Actually, might have been chapter 2 or something such. So atomic radius is going to decrease across the periodic table, or across a period, or should I say, in the periodic table. Across a period, what happens is that the number of protons increases while shielding stays the same. Now, if we go back for a second and we remember what are the three factors that are going to affect and most of these physical properties, number one was proton number. So number of protons. So whether there are 2 protons, 10 protons, 24 protons in the nucleus. Number two was shielding. which, if you remember, shielding is the repulsive effect of inner electrons for outer electrons. And then number 3 is going to be distance from the nucleus. Oh. Now, for this particular conversation of atomic radius, we're going to talk about the number of protons and the shielding. We're not going to discuss distance from the nucleus because the radius is the distance of the outer electrons from the nucleus. So we will be essentially being a little meta there and talking about the distance while blaming on the distance. So we're really only going to focus on 1 and 2 for atomic radius, but we'll look at all 3 of them for other properties. So for atomic radius, as we go from left to right across a period, so for example, if we go from sodium to magnesium to aluminum, silicon, phosphorus, so on and so forth, the number of protons in those atoms is going to increase, but the shielding is going to stay the same. Remember that shielding stays the same for elements in the same period. So shielding stays the same because they're in the same period. Elements in the same period have the same shielding because they have the same number of valence valence shells. So they have the same number of energy levels here. So shielding is the same because they're in the same period. But the number of protons does increase. This increases the effective nuclear charge, or the amount of pull the nucleus has for those outer electrons. And because the pull for those outer electrons is stronger, the atom is going to decrease in size. So for example, for sodium has 11 protons in its nucleus, with again the same shielding as everything else. Chlorine, on the other hand, has 6 more electrons. So that's 6 more protons. So that's 17 protons in its nucleus. The 11 protons in sodium are going to pull those valence electrons less than the 17 protons in chlorine. Because the 17 protons in chlorine pull on the outer electrons of chlorine more than the 11 protons in sodium, and again, like we said, as we go across a period, the number of protons in the nucleus goes up, the chlorine atom is going to be much smaller than the sodium atom because of that internal pull for the outer electrons. But again, sodium and chlorine are both in period 3, and because they're both in period 3, their shielding doesn't change. They have the same number of valence or of energy levels. And so that's why that atom decreases in size. On the other hand, atomic radius increases down a group. Why is atomic radius going to increase as we move down a group? Atomic radius is going to increase as we move down the group because there are now new energy levels added to the atom. Now, this is a little more straightforward. New energy levels also add extra layers of shielding, which is going to lower the effective nuclear charge felt by the other electrons. Not to mention that there are now more physical layers to our atoms, so they get larger. So as we go down the group, the atoms get larger and larger and larger. And that's because as we go down the group, we add energy levels to that atom. As we add energy levels to the atom, there are now more layers between our proton in the nucleus and the outer electrons. And so those electrons are pulled much more weakly by the nucleus because of the shielding provided by those inner energy levels. So as we go down the group, the atoms are going to get larger because the pull of the nucleus, what we call the effective nuclear charge, which is just the pull of the nucleus for those outer electrons, is going to be weakened by the extra layers of shielding. Now, we do need to be able to read these kind of graphs of this data. We can visually see here how the y-axis is the atomic radius and the x-axis is the atomic number. And as we go from left to right, from sodium to argon, across the period in the periodic table, we can see how those atomic radiuses actually decrease in size. And we can see that in the graph. So if we were to show this without the elements at the bottom, you should be able to see that all these elements are in the same period as their atomic radius decreases. Now, to give you a better visual here, we can see that here in this visual representation of the atomic radius of the elements, we can see how if we go down one of these groups, like group 1 or group 18 or even groups on like 16, we can see how those atoms are going to go from smaller to larger as we go down the group. But then as we move across a period, like across period 3, those atoms are going to get smaller because of that increasing proton number. So this is a visual representation of that pattern that we just talked about. Now this is atomic radii. We can talk very similarly about what we call ionic radii. Ionic radii is simply just the radius of a charged particle or an ion. It still has the same idea, the same basic concept of the size of the ion in this case. But we're not going to compare so much the ions of one element to another yet. We'll look at that in a second. But we first need to talk about the two different kinds of ions. Cations are always going to be smaller than the neutral atom of the same element. And this is due to the fact that the cations are losing electrons. And when they lose those electrons, generally speaking, especially with representative elements, they're going to lose energy levels. This means that those cations are losing shielding, and the nuclear charge is going to remain the same because the number of protons doesn't change. So let's take the sodium ion as an example. When we have a sodium atom, we have 11 protons in the nucleus with 11 electrons. And those electrons are found in 3 different energy levels, 2 in the first, 8 in the second, 1 in the third. When sodium becomes the sodium plus cation, that last energy level is removed when we remove the 1 electron. That means that the new outer shell, which is the second energy level now, is going to be closer and have less shielding because there's only 1 energy level between that and the nucleus. But the number of protons stays the same, there's still 11. So these protons, because of that extra layer of shielding, are going to attract the valence electrons a lot more strongly, creating a smaller cation than the original atom it was made from. On the other hand, when we look at an anion, and we'll take chlorine as an example, the chlorine goes from having all of these electrons to now having an extra electron when it becomes an anion, the Cl- anion. Anions are always going to be bigger than the neutral atom of the same element. So this Cl- anion is actually bigger than the Cl atom. And the reason for that is a little more complex. This is going to be due to the fact that the anion is gaining electrons. And so even though the number of protons doesn't change, the number of electrons in the electron cloud is going to go up by as many charges as we have negatives. Since the nuclear charge remains the same, but the outer shell is now more saturated with electrons, the electrons in that outer shell are going to repel each other more strongly. That extra negative charge from the electron that we added is causing more repulsion between the electrons, both inner electrons and electrons in the same energy level. That repulsion causes this ring to grow and to push out. And that's what makes the anion bigger than the parent neutral atom. The extra repulsion from that added electron is going to push all of these layers out a little bit, creating a larger ion than the original. Now that's ionic radius, right? That's ionic radius compared to itself. So the cation to its original atom, the anion to its original atom. What about compared to each other? So there are trends in ionic radius, although they are a little harder to see. In ionic radius, we have to consider the relationship of the parent atom and its original atomic size. Ionic radii are going to decrease from left to right across the period. However, the decrease is not due because of anything that is unique to the ion. That decrease is due to the size of the neutral atom from which it was made. We saw that in the prior conversation. Sodium is going to be bigger than magnesium, which is bigger than aluminum. And as we go across the period, the atoms get smaller. And that's because of the number of protons in the nucleus. Well, from left to right across a period, the size of the ions decreases. But that's just simply because that parent atom, the neutral atom we were talking about earlier, is also going to get smaller from left to right. So it's just a result of atomic radius. However, what comes in that is new when we talk about the size of the ions and the ionic radii instead of atomic radii is that now we see this large jump from group 14 to group 15 in period 3 specifically. Although this jump is going to be mimicked just slightly in different groups with other periods. That large jump happens when we change from making cations to making anions. So we can see here in this x-axis that from sodium all the way to silicon, we are creating cations. Sodium has a +1, magnesium +2, aluminum +3, silicon +4. But then once we go to period or group 15, we start making anions. So P is 3 minus, S is 2 minus, Cl is -1, argon is neutral. So the size of the ionic radii, there's a big jump here. Why? This jump is due to the change from the cation to the anion. Remember, cations we discussed not that long ago, a few last slide. We discussed how the cations are going to be smaller than the original, whereas the anions are going to be bigger than the neutral atom. So that's why we have a divide here. From the cation side, the cations have in general a smaller radius than the anions because they shrink when they're made, whereas anions get larger when they're made. So this trend of the jump happens because of the cation versus anion difference. However, the trends within the cations and the anions, this trend right here and this trend right here, happen because of atomic radius and the trend in atomic radius. So we have to keep that in mind. We wouldn't see this jump with atomic radius comparisons, but we do see it with ionic radius. And then finally, ionic radius increase as we go from top to bottom down a group on the periodic table. And again, this is very simple. This is due to the increase in size of the neutral atom that make up the ions down the group. We discussed how down a group on the periodic table, the atoms get larger, the atomic radius gets larger because of the added shielding. Well, the same thing is going to happen to the ion that is made from those atoms. So this is just, again, due to the atomic radius trend. So in essence, ionic radius is going to be or behave exactly like atomic radius, with the exception that across a period, we see this large jump because of the difference between anions and cations. Whereas cations got smaller than the neutral atom, that's why they're lower down, and then anions got bigger than the neutral atom, that's why they're higher up. So let's look at a visual representation of this. We can see that in numbers here, and we can see it graphically here. But let's look at this visually, right? A visual representation. So here we have group 1 elements and their ions. We can tell here the ion is in gray, and then in the colored circle is going to be the atom, the neutral atom. The blue ones are metals, yellow is semi-metals or metalloids, and the beige is non-metals. So you can see how for the metals, which form positive ions, and for a lot of the metalloids, which form positive ions, we can see how the ion in gray is smaller than the neutral atom in blue. And that's because, again, cations are going to be smaller than the parent atom because they lose a layer of shielding, and so the effective nuclear charge is larger. But once we get over to the non-metals and some of the metalloids, which form negative ions like O2 minus, Cl minus, Sc2 minus, we can see how now it's inverted. The gray that represents the ion is larger than that beige color that represents a neutral atom. And again, that's because the neutral atom is going to be smaller than the ion that is formed. Or to say it backwards, like we said earlier, the anion that is formed is bigger than the parent neutral atom. And we can visually see that here. And then you can see as we go move across this, how the ion, if we focus on the gray, from sodium to magnesium to aluminum gets smaller. And again, that's just due to increased nuclear charge and the atomic radius trend. But then as we jump over to phosphorus, which has a negative charge for the ion, that ion suddenly gets much larger than the one for silicon and aluminum. But then again, it starts to decrease again as we move now across the negatives. All right. So let's discuss a physical property that we haven't discussed before, electrical conductivity. Now, electrical conductivity of metals is going to increase across a period. And this is very important. We need to talk about electrical conductivity, but as it applies to specific elements like metals, which conduct electricity under any state of matter. We can't really talk about the conductivity of things like chlorine or argon because they're just simply gases that don't conduct electricity at all. So when we say that the electrical conductivity of the metals increase across a period, we are referring to only that of the metals, that of the elements that will conduct electricity at the solid state. In general, across a period, what's going to happen is that the charge of the metal is going to increase. Sodium, for example, if we keep taking period 3 as an example, which you might notice throughout this chapter, period 3 is kind of our go-to example for a period, but these discussions apply to really any period. So if we look at period 3 metals, sodium, magnesium, and aluminum, sodium has a +1 charge, magnesium has a +2 charge, and aluminum has a +3 charge. The higher charge means that the sea of electrons in the metal is more full. Sodium has a 1-to-1 ratio between ions and the electrons, whereas magnesium has a 1-to-2 ratio and aluminum has a 1-to-3 ratio between the ions and the electrons. And that's because remember that the electrons in the sea of electrons of a metal come from the atom losing those electrons to gain its charge. Well, the larger the charge means the larger the sea of electrons, and the larger the sea of electrons means that the more electrons are there to conduct electricity. Remember, electricity is just a flow of electrons through a metal. So if we have more electrons in a metal, that's the reason we'll have more electricity. The electrical conductivity is going to drop drastically across a period once we get to the metalloids and then to the non-metals. Remember that the metalloids, like silicon, are going to be semiconductors. And so they do still conduct electricity, but need special conditions, like high heat, to do so effectively. And then most non-metals are not going to conduct electricity whatsoever, or have very, very poor conductivity when they're solid, like phosphorus and sulfur. Chlorine and argon, being gases, are incapable whatsoever of conducting electricity. So the metalloids are going to conduct some electricity, but very poorly, and the non-metals are going to be horrible conductors if they're even solids. So as we move across a period, the conductivity of electricity goes up across the metals, but then once we get to the metalloids, it decreases drastically, and then across the nonmetals as well. So mostly because the nonmetals and the metalloids don't have a sea of electrons. Another point that we've discussed, but not as a trend, is melting point. The melting point of the element is going to be dependent on the type of structure that the elements have, which we discussed in chapter, I believe, was 5. Metals have a high melting point because of their strong metallic bonds. So when we're looking at the left side of the periodic table, those elements are going to have very high melting points because the bonds, the lattice, the metal lattice, is going to be held together by metallic bonds. So just backtracking a little here, the metallic bond, which is the force of attraction between those cations and the sea of electrons, is a very strong bond. And that means that it's going to take a lot of energy to separate those ions. The larger the charge of the metal, the stronger the attraction between the ions and the sea of electrons. And this goes along as well with the size of the ion. The smaller that ion is, the stronger the attraction between ions and the sea of electrons because of the reduced distance between the charges. So smaller metals with larger ion charges have a stronger bond and therefore a higher melting point. So that means things towards the top of the periodic table, which are smaller, and towards the right side of the metals, which have a higher charge, are going to have much higher melting points. So going back to this chart, we can see how something like aluminum, which is, let me change the color here. So the aluminum, which is very small ion and a very high charge like +3, is going to have a high melting point, while something like gold, which is very large compared to the other metals and has a very small charge like +1, is going to have a low melting point. So in general, ions that are higher up and to the right, which are smaller and usually more highly charged, are going to have much higher melting points than ions of metals that are bottom and to the left, which are very large and have a very small charge. Now, take this with a grain of salt, right? Because we do have the transition metals here. As you can see, the metal ion sizes vary, as do their charges. We can see here that something like molybdenum has a +4 charge, which is huge. And it's actually a fairly small ion. And we wouldn't expect that because it's farther to the left and, farther down. So do take this with a grain of salt. This mostly works for the representative metals, but, can be applied if we know the charge and the size of an ion. Now it's for metals. If we have something that's giant molecular structures, we're going to have high melting points due to strong covalent networks. So things like diamond and graphite, they're going to take a lot of energy to break and melt because the covalent bonds holding up the giant molecular structure that we discussed earlier in the year is going to take a lot of energy to separate. That's why diamond has such a high melting point. All of those covalent bonds in the network make it really, really hard to separate all the carbons. Finally, simple molecular structures, which tend to be on the right side in the non-metal section of the periodic table, have extremely low melting points because they're held together with intermolecular forces. Remember that if we have simple molecular structures, we're not separating bonds like we are with metallic compounds. We are separating intermolecular forces when we melt them. The weak intermolecular forces that hold the molecules together don't require a lot of energy to break. In fact, a lot of these non-metals on the periodic table that are simple molecular are going to be gases already at room temperature. All simple molecular elements have London dispersion forces. And that's because when we are looking at an element, we're looking at just one element, and therefore there's no polarity. So whether we're looking at nitrogen and it's N2, gas, or we're looking at argon and it's just Ar gas because it's a noble gas, or we're looking at something like sulfur and we're looking at S8S, or because we're in Cambridge, just S, sulfur 1, or even phosphorus P4, which is also solid, or just P solid in Cambridge, most Cambridge reactions. We're looking at just one element, even if it is bonded, like in a diatomic or tetratomic or octatomic molecule, we're looking at a simple or a single element. And so we're going to look at London dispersion forces because everything's going to be nonpolar. So the larger the element, because we're only looking at London dispersion forces, the larger the element is, and the larger the molecule is, the higher its melting point is going to be. Which is why things like S8 and P4 are solids, which have a lot of atoms, but things like N2 and argon are gases, which are very just one or two atoms in them. Not only that, it also helps explain the halogens. If we have F2, Cl2 going on the period, Br2 and I2, we see that fluorine and chlorine are gases at room temperature, and that's because fluorine and chlorine are small and not very heavy. But bromine, Br2, is a liquid at room temperature. Why? Its melting point is much higher because the bromine atom is bigger. As we go down the group, the atoms of the halogens get larger and larger and larger. And because the atoms get larger and larger and larger, their melting points get higher because the London dispersion forces are stronger. So bromine is a liquid, and even I2 is a solid at room temperature. Because the iodine atom is so large, it creates really strong London dispersion forces, which make it have a really high melting point compared to the other molecular compounds. Of course, this is still a simple molecular structure. It is not going to be as high a melting point as something like diamond or even some of the metals, but it is going to be higher than most other non-metals. So that's the trend in melting points. Now let's look at how this creates a pattern. Melting point patterns are going to appear based on the type of structure the elements have. So the melting point of metals across the periodic table generally is going to increase because as we move across the periodic table, there is a trend to have a higher and higher charge for the metals. So as the ion charge increases and as the size of the ion decreases because we're moving from left to right across a period, that is going to create stronger metallic bonds and therefore larger melting points. We can see that with sodium, magnesium, and aluminum. If we look at this section of the graph here, we can see that for, oops, I am using the wrong thing. So we can see as for sodium, magnesium, and aluminum, in general, that melting point is going to increase. And again, that's because these are metals. And so we have metallic bonding. So here, this is going to be metallic bonding. And the charges are going to increase. It's +1, +2, and +3. And the sizes do get slightly smaller. Once we get to something like silicon, however, we're no longer dealing with a metal. Instead, silicon is a giant molecular structure, just like diamond. So silicon is giant molecular. Because silicon is giant molecular, you can see how that melting point is the highest out of anything in its period. And that's because we work in covalent bonds if we want to melt something like silicon. But then once we get past silicon and we get into the realm of things like, let's go here, things like phosphorus, sulfur, chlorine, and argon, these now are very low. Why are these very low? Because they're not metallic, they are not giant molecular. These are going to be simple molecular. And because these are simple molecular, we are dependent on intermolecular forces, specifically London dispersion forces. So what happens, as these get larger, they're going to have higher melting points, like the sulfur, which we discussed as S8, and phosphor, which is P4. But then things like chlorine and argon, which is Cl2, and just Ar, are going to have very low melting points, because the only things that are going together are those intermolecular forces, which are very weak as they get smaller. So each section here, depending on what type of structure it has, will have different reasons for the melting points. And again, we can see here the melting points of the elements, how we go from 300s, 900s for the metals to 1600 for silicon. It jumps really high up, and then back down to the 300s, and then lower and lower and lower for the non-metals. And that, again, we can see here because of their type of structure. Sodium, magnesium, and aluminum are giant metallic. Silicon is giant molecular. And then phosphorus and on are simple molecular. And so we have to take different things into account. So the next conversation we're going to have is one we've had extensively at a previous chapter. So we're going to very briefly discuss it, and that's ionization energy. Now remember, ionization energy is the amount of energy needed to remove electrons from an atom and creating positive ions. So when we talk about ionization energies, there are multiple ionization energies. Usually when we discuss a pattern on the periodic table, we will discuss first ionization energy, which is the energy needed to remove 1 mole of electrons from 1 mole of an atom of an element in the gaseous state to form 1 mole of a gaseous plus 1 ion. This is a definition we learned earlier in the year when we had the discussion about ionization energy. Ionization energy is mainly dependent, like a lot of these things, like atomic radius, on the 3 factors we discussed earlier. The size of the nuclear charge, meaning the larger the nuclear charge, the more tightly held the balanced electrons are. So the more electrons we have in the nucleus, the more protons we have in the nucleus, the more attracted the outer electrons are for the nucleus. The second is the distance of the outer electrons from the nucleus, which is going to be related to that property we discussed earlier, which is atomic radius. The farther away these electrons are, meaning the bigger the radius of the atom, the more loosely these electrons are going to be held, because distance diminishes magnetism. Think of like a magnet in a fridge. The farther away you hold a magnet from the fridge, the less attracted that magnet is. If you're too far away and you drop your magnet, it's just going to fall on the floor. But the closer we get that magnet to the fridge, the closer we get to opposing charges, the stronger the magnetism feels. And we can see that by the widening of this arrow. And so the stronger the pull is going to be. So the larger the atom is, the more loosely held those electrons are. And then shielding. Shielding is the effect of the repulsion of the inner electrons. The inner electrons in an inner shell, not the valence shell, not the outside one, but the inner ones, are going to repel those valence electrons, essentially opposing the attraction for the nucleus. The more inner shells there are, the more repelled the outer electrons are, and the more loose they're going to be, the less attracted to the nucleus they are. So this goes hand in hand with the distance of the electrons, because the farther out this outer shell is, the more inner energy levels we're going to have. The farther that distance becomes, like potassium versus lithium here, the less attractive that electron is, but also the more rings, the more energy levels we're going to see between them. Those energy levels in the inside are going to repel the ones on the outside, like we see here, and therefore are going to loosen the grip of the nucleus for that outer electron. The more loosely held the outer electrons are, the less energy it's going to take to remove them, and so the lower the ionization energy is going to be, especially the first ionization energy. So what are the 5 patterns that we saw earlier this year when it comes to ionization energy? And this is just an overview. Again, you can read more about this. You can go back and review and watch that video. But in general, as we move across a period from left to right, the ionization energy is generally going to increase for an element. Nuclear charge, as we move from left to right, is going to increase while shielding remains basically the same because we have the same number of energy levels. As you go from the last element on one period to the first element on the next, there's a rapid decrease in ionization energy. So as we go from something like, and I'm going to go forward for a second, like neon, which has a really high ionization energy, first ionization energy, to something like sodium, there's a large decrease. And you can see how the right end of the periodic table has a much larger ionization energy in general than the left side. And that's because of shielding. As we go from one energy level to the next, one period to the next, we're adding an energy level. So neon only has 2 energy levels, while sodium has 3. Argon has 3 energy levels, while potassium has 4. That addition of the extra energy level is going to increase the shielding effect and therefore make that outer electron much more loose. As we go from group 2 to 13, there's a slight decrease in ionization energy. New electrons are going to be found in the p subshell instead of the s subshell as we go from group 2 to 13. Because the s subshell becomes full, then the group 13 is going to have to put those electrons in the p subshell. And that's going to cause an increase in distance, a very slight increase, but an increase in distance because the p subshell is slightly bigger. And that's going to provide a small amount of repulsion for the p electrons, causing that drop, that slight decrease in ionization energy. Now, like I said, we have discussed this before, and you can always go back to the chapter 2 videos in order to look at the more specific explanations of these patterns. As you go from group 15 to 16, there's again another slight decrease. So these 2, 3, and 4 are kind of the exceptions to the rule that as you go from left to right, there's an increase in ionization energy. And as we go from group 15 to 16, the reason why there's a slight decrease is that we're adding new electrons to the p orbital, not sublevel, but orbital, and it causes spin pair repulsion. And so that spin pair repulsion makes it easier to remove that electron in group 16 than it is in group 15. And finally, as you go down the group, the ionization energy of the elements decreases. And this is because the distance from the nucleus and shielding is going to increase. As we add new energy levels going down the group, from 2 to 3 energy levels to 4 to 5, that added energy levels are going to increase shielding, and they're also going to increase the distance of the atom, the size of the atom. The number of protons increases, but it's outweighed by the shielding and the distance, and so the ionization energy is going to go down. And we can see all those patterns here. We can see how going down a group, the ionization energy is going to decrease, how going from left to right across a period, the ionization energy increases. We can see that drop between nitrogen and oxygen for the spin pair repulsion, as well as between beryllium and boron, or magnesium and aluminum for that p subshell. And here is the graphical version of that pattern. We can see as we go from sodium all the way to argon, which is across period 3, which, like I said earlier, is our kind of guinea pig that we use as an example, but this applies to all of the groups. We can see how that ionization energy, first ionization energy, increases. But we can see how between groups 2 and 13, magnesium and aluminum, there's a dip, it goes down because of that p sublevel that's being filled, and how across 15 to 16, from phosphorus to sulfur, there's again a decrease because of spin pair repulsion. And you will be given these graphs. You need to make sure that you learn how to read graphs, because you will be given this graph and I'll be asked to explain why is there a dip between P and S. And using words like spin pair repulsion, decrease in the amount of energy needed to remove the electron because of spin pair repulsion, and being able to verbalize those explanations. So like I said, this is all a review for the ionization energy part. I hope it was helpful, and you can always go back to chapter 2 videos to get the more in-depth explanations. But it's it for chapter 10, section 2. I will see you all in the next video to start discussing the trends in chemical properties.